Well, welcome to another exciting day here at Spain Park. It is Tuesday, March the 30th. And today we're going to begin talking about the different states of matter. Mainly the three ones. Now there are five. Does anybody remember what the five are? Plasma and Bose-Einstein condensate. Okay, we're not going to worry about those because they're at very extreme conditions. Okay. So we're going to just talk about kind of solids, liquids, and gases. And I have for you kind of a fill-in notes for this, and we're going to go through it super fast because a lot of this is common knowledge, previous knowledge from like second grade. And so,
You say that.
at least the beginning part of it.
It's 30 days, fall, September, April, June.
Start calendar. Because it's like January, April.
Okay. So, when we're looking at this, we're going to kind of go through here. We're going to fill in much of this. Ideally, we're going to get through this whole sheet today. Now, that's my utopian world. My real world, I mean, that's not probably going to happen, but I can dream. All right, so solids, liquids, and gases. What a big deal. Now what we're going to do is this is chapter 10, we're going to combine it with chapter 11. And so, yes. So, I didn't know if it came on or not. And so, we're going to do this together, but chapter 10 is just going to be this quickie. There is going to be a little bit of math in it. Whether we get to that today, probably not, but we'll probably spend Thursday doing the math. And then we'll decide whether or not we're going to do an exciting lab where we watch ice melt.
Oh, that's so cool. Yay!
Do we get to watch paint dry for that?
So that's the second part of the lab. All right. So we're going to fill in these blanks. So let's just see. Now some of this at the very beginning goes back to our attractive forces. Okay, what are our three types of, first off, what are our four types of substances, types of bonds, that a substance can have? If it's a metal and a non-metal, it's going to be?
Ionic.
No, metallic's going to be what?
Just metal.
Just a metal, just a pure metal, gold, silver, copper. Okay, so we got metallic.
Ionic.
Ionic, which is your metal and your non-metal, where the electrons are transferred. Then we have when they're shared, covalent, but there's two types of covalent. You got covalent network, which is that small group, diamonds, graphite, silicon dioxide, silicon carbide, and just silicon. Or covalent molecular, where it's just all the rest of the covalent substances that form individual small molecules. Okay? Ionic, metallic, and covalent network all have real strong bonds. So if you're gonna melt those, change a solid into a liquid, you're gonna have to break an ionic bond, a metallic bond, or a covalent bond. Well, what types of bonds do you break between molecules? What are the IMFs, the intermolecular forces? London dispersion, hydrogen bonds, and dipole-dipole. Okay, are those strong or weak? Those are very weak attractive forces. So those substances tend to be liquids or gases. So, what determines whether the state of the substance is a solid, liquid, or a gas? What do you think goes in there?
Strength of the bonds.
The strength of the bonds holding the atoms together. The strength of the bonds. Okay? So ionic, metallic, and covalent network substances have what type of bonds holding them together? Strong or weak? Strong. So what state are they going to be at room temperature? Solid. Covalent molecular substances only have strong or weak? Weak bonds. So they are generally what? What states? Liquids or gases. Okay? The force, what's the force called holding just non-polar molecules? This is the only force between non-polar molecules. London dispersion. Can I just put LDFs? We'll know what that is, LDFs. It's London dispersion, but I'm just going to say LDFs. Okay? And are the blank of all the forces. The weakest. See, I told you this was going to be... Now, this isn't second grade stuff, but this is all review of everything that we've done before. Okay? We're just kind of going through it and reminding ourselves. What type, polar molecules have what type of intermolecular forces? Dipole-dipole. We'll say dipole, dipole. This is really supposed to be your LDFs blank. We'll say LDFs and possibly hydrogen bonds. These bonds are stronger, which means their boiling points will be higher or lower. Higher. It's going to take more energy to break them apart. Okay? But it's still going to be way, way weaker than these. Okay? Because remember, those IMFs are only about 1/10, 1/20th the strength of an ordinary covalent ionic bond. Okay? So will be higher than nonpolar molecules. Okay? So what do we know about the shape? Molecules of a liquid have, this is the second grade stuff.
No definite shape.
No definite shape. But what about their volume?
Have a definite volume.
They do have a definite volume. So if I take, this gallon jug of water and I put a hole in it and it all spills onto the floor, it's still a gallon of water. The water molecule is still going to occupy the same space. It's just going to be all flattened out all over the floor. Okay? Because the molecules are still basically right next to one another, and so they're going to occupy the same space. They don't compress, they don't expand. Okay? Liquid molecules have enough energy to bend and stretch the bonds holding them together, which allows them to be able to move, but there's a different word that starts with an F. Flow. Now, when I think about flowing, liquids flowing, I think about marbles in a jar. And then you start to pour the marbles out of the jar, and you can see the marbles rolling around one another as they come out of the jar, right? That's when you pour a glass of water or something, the water molecules are just rolling over top of one another coming out. Same thing if you had a play or some kind of musical, and you see the fog that's coming over the stage that they make, the smoke machines, is rolling. Those molecules are just rolling over one another. Okay? It's because the molecules have enough energy to kind of stretch their bonds. They're not stuck in place. Liquids and gases can flow. Liquid molecules are also still right next to one another, so they cannot be pushed any closer, which means, what's the word mean? You can't push them any closer. If you push a gas closer, you're going to compress it. So the opposite of that is incompressible. And we've talked about this before, and this is how y'all are all starting to drive. This is how your brakes work. you have brake fluid in your car. When you push on the brake in the car, that force is pushed via the liquid all the way to the 4 tires, which then pushes the pistons, which actually can, you know, then squeeze on the tire and make you stop. Okay, but the force is applied here because the gas liquids are incompressible. The force gets transferred all the way down as if it were like on a solid rod. But this way you could put the, you know, you can make a curve and go around and twist the cable, no, not the cables, but the hoses, anywhere you need to get to the brakes. Pretty ingenious. Okay? So far so good? Nothing deep here, right? All right. Zooming. Like an advanced level class should. Halfway through the first page, look there. Okay, which are more dense generally? Gases or liquids? I mean, liquids or solids? Liquids are less dense. Okay, because they're moving faster and have greater vibrations. But which one's the major exception to this? When you finish reading it. Water, which is why when it freezes, making ice less dense than liquid water. The trend is, I'm going to put H2O.
Why does that happen? Like, no one knows.
Yeah, no, it's real obvious. It's hydrogen bonds. Okay, so here's water molecules that actually form, because of hydrogen bonds, they form these hexagonal rings. So when it freezes in this shape, which is why all snowflakes have 6 points. Okay? Because of the hydrogen bonds forming this hexagon. And then another one comes in and the hexagons all just kind of link together. And then so you get a bunch of them. Okay? Whoops. I'm spilling water everywhere. Okay? So when this is as a solid, now see the big opening in the center. So, but as a liquid, they can stretch and bend and they close that gap. And so they're more dense, they're closer together as a liquid than they are as a solid because of the formation of the hydrogen bonds. Now that's very rare. Most substances, just as you cool them down, you slow them down, the molecules just get closer and closer and closer and form their crystal structures. Just because water forms an open crystal structure, it's one of a handful of substances. Bismuth and I think tungsten. I know bismuth is another one. I'm not sure. I always look them up and then I can never remember them because they're not common. Okay? But again, we thank God for this because if water did not expand when it froze, there would be no life, nothing could live in the lakes and ponds and streams and oceans in the north because everything would freeze solid. And everything would die after one winter, okay? But because the ice floats, it sits on top, and then it kind of makes insulation so the rest of the water doesn't freeze. Anyway, very, very unique. Surface tension. Now, I hope I can carry this without messing it up. I have right here. Can you guys see? What's happening?
The paper clip is sitting on top of the water.
Paper clip is sitting on top of the water. Okay, hopefully you can see that. Paper clip is sitting on top of the water. Now if I take a different paper clip, same type of paper clip, and put it in this way, it goes right to the bottom. So the paper clip is way more dense, but yet it sits on the surface. Does anybody know why?
Surface tension.
Okay, well what would that be? Oh, I just shook it and it fell.
Is it the way that like water molecules form? Because like on the top they can't be like cold. It's like a hard layer. So
That's exactly right. I think we've talked about this previously again. there's a better picture than what I'm going to draw in your book, but if you look at a water molecule right here, okay, in the middle, it's got dipole-dipole hydrogen bonds attracted. It's going to be attracted on all sides, every which way but loose, all the way around, okay? Evenly pulled in all directions. So they're just kind of bouncing off one another, going every which way. But on the surface, if we have an H2O molecule up here, it's only getting pulled this way, this way, this way, this way, and that way. There's nothing pulling it upwards because there's nothing above it. So as a result, there's an unbalanced force, so an inward and downward force that forms a skin across the top. That's called surface tension. That's why when you dive into the pool from the high dive, you put your hands out in front of you because you need to break the water molecules. Once you get past this thin layer, then it's smooth sailing. It's no problem.
So that's when belly flops hurt.
That's why a belly flop hurts, because you're hitting so much surface area and it's not giving. And that's again why I had to put the paper clip this way, flat, to make it stick on top of the water. Go vertical, then you have a whole, you don't have enough surface area to support the weight. And even then, it's very precarious. It takes forever to make that paper clip float. Okay? So surface tension this is why the bugs can float across, on top of the water, because of surface tension. That's why, again, if somebody jumps off a bridge, it's too high, you're going to have serious damage because you're going to hit, they say after so many feet, it's like concrete, the surface tension. So, we talked about with soap, detergents, what they do is they get in between these molecules and help break down these attractive forces here, and so they lower the surface tension. So when your clothes has the water going across the little pores, it breaks that down and lets the dirt escape out rather than getting the film over it. Okay, so they're called surfactants. A thing that breaks down surface tension is a surfactant. That's what detergents are. Okay. There was this detergent called Surf for a while, and everybody thought, "Ooh, it's a cool name, it's Surf, Surf's Up." But it really was just short for surfactant. Okay? All right, so surface tension is caused by the blank attractions. What did I say?
It's like unequal.
Unequal or uneven. Okay? Attraction on the molecule on the surface of a liquid. This creates a type of skin which holds everything together. Now, cohesive forces are attractions in between. This is something you learned in like 7th or 8th grade. Cohesive forces. You got cohesive and adhesive. Have you ever heard the term adhesive? Like adhesive tape? What does tape do? It sticks to everything else, right? And itself, but it sticks to everything else. So adhesive forces are attractions between two different things. So what are cohesive forces going to be? Attraction between like molecules. Okay? Or between similar, or let's just say like molecules, while adhesive forces are attractions between different molecules. Okay? Now water gets to the top of the trees. It's a form of this. It's kind of a combination of this. Anybody know how, like a big oak tree, how does the water from the roots get up to the leaves at the very top?
The same way a paper towel works.
The water pulls itself up.
Yeah, like the same way a paper towel works.
It's just, okay, it's called, do we know what that's called when it kind of wicks its way up? It's a big word. Begins with a C. What are the little tiny veins, the connections between veins and arteries called? Capillaries. This is capillary action. Okay, now let me just show you how that works. Here's your tree, the roots, okay? Water has a combination of adhesive and cohesive forces. So the adhesive forces make the water attract up the side of the root. Actually, the tree has little veins, okay, that's carrying the water up. And so it's attracted to the sides of the vein by adhesive forces, but then the water molecules are being stretched apart, and those hydrogen bonds then want to get, oh man, I want to get, and so they pull it back together again. Then it inches its way back up again, the side, and then it pulls back close. So it's kind of an inchworm type motion up. Now it doesn't, it goes real smooth. I don't know if they do this anymore, but back in the day, they would, if they needed some kind of blood type, or I think even when I just went and gave blood and they typed my blood, they prick your finger, it has a little drop of blood on it. Then they have a little tiny little glass tube that they just put right onto the drop. And just by capillary action, the blood goes up into that tube. Okay? It just rises up, and then they can use that to sample to test, for the types, and if you have any kind of disease or something. Okay? So capillary action is it's the combination of adhesive and cohesive forces. Adhesive, cohesive, working its way up until the weight of the liquid equals gravity coming down. Okay, so you got to balance those out. So the more narrow the tube, the taller it can go, because the weight is going to be less. So you still have that same attractions, but the weight will be less. So the capillary tubes are usually very, very, very narrow, so they can get the maximum height of them. So the little veins in the tree are very narrow. Plus, like you said, there is some respiration, I think is what it's called, transpiration, when the water evaporates out of the leaves, and then that kind of creates a vacuum, which then kind of does help pull the liquid up a little bit as well. All right. So water is attracted to the sides of the veins in the tree by, no, capillary action is here. What type of forces? No, but to the sides. That's adhesive. And then to itself by cohesive. Okay? So there's just some definitions of capillary action, of surface tension, just to have an idea why liquids have those properties. Okay? Now, the stronger the attractive forces between the molecules, the greater the surface tension is going to be. So mercury is very strong because it's so big. Its surface tension is going to be way greater than this. As a matter of fact, mercury's cohesive forces are so great and its adhesive forces are so weak that mercury is considered a dry liquid. So if you put mercury into a glass bowl and you roll it around, the mercury doesn't stick to the sides like water does. It just all comes back together again. You guys probably have never ever seen the Arnold Schwarzenegger Terminator, I think it's Terminator 2. No? Okay, they have the metal man in there that, yeah, okay, so Arnold froze him with liquid nitrogen, and then he shattered. Okay, and then so he's on the ground, but he's all shiny metal. But then as it begins to thaw, then all of the things all started running back together. And I saw a special on how they filmed that, and they actually used mercury, and they just kind of showed the mercury, drops kind of all coming back together, because their cohesive their cohesive forces are so strong, it just comes and goes back and forms this sphere. So mercury in a glass tube, you know how water makes the curve, which we call meniscus, it's this way. Mercury's meniscus is this way because it's way more attracted to itself than it is the glass. Water's meniscus is because it's attracted to the glass.
So
It's adhesive forces.
Where would you measure mercury?
From the top of the from the top. Okay, the highest point. All right. So good stuff. practical stuff. Go out in the world. It's going to be another one of those cases where you're going to look at something and you're going to think about it, and then you're going to say, I can't believe I'm thinking about that. But then you're going to say, well, it really is cool. Okay, but you just won't admit that to any of your friends. All right, and that's totally fine. All right, the natural spreading out of one substance through another. So if I opened up a bottle of perfume and it spread out into this room, what's that called?
Diffusion.
Diffusion. Okay, why do gases naturally diffuse, spread out?
They're like free flowing atoms.
Okay,
They
the
fill
free.
in whatever's around.
Okay, they're in the result of the rapid random motions. Okay, which is the same as free flowing. So now this just makes sense. Bigger, heavier molecules will spread out faster or slower than small molecules. Slower. If you have a big mass, you ain't going fast. Trust me, I know. Okay? If you have a big mass, you ain't going fast. So they spread out slower than smaller, lighter molecules. Now, as the temperature of the substance increases, the molecules move. Okay? What's my other word here? Oh. I didn't read the rest of it. It increases the rate, in other words, the rate of diffusion. So in other words, if the room is hot, the gases are going to spread out faster than if the room's cold. All right, now, we're going to take a little pause from this, and we're going to look at a graph. Temperature measures the average kinetic energy. Does anybody remember from 8th grade science what kinetic energy is?
Energy of motion.
Very good, energy of motion. Okay? So temperature measures,
That was not a good time. That was a brutal 3 or 4 weeks.
It's here somewhere. Okay? We're gonna elevate our math skills a little bit. Okay? To calculus.
We're not doing numbers and that.
No, this is a theoretical thing here. Okay? No actual doing it. Yeah, I got poison ivy all over my arm. That's why I keep scratching. I'm going crazy. This is the same gas at 2 different temperatures. Now, notice it says number of molecules. In Algebra 1 and maybe Algebra 2, you learn how to get the equations of a straight line. Do you have to maybe do hyperboles and parabolas, and sometimes in Algebra 2, maybe, okay? Calculus is able to calculate the area under the curve, okay? It's called taking a derivative of the function, okay, but that's irrelevant. You can just imagine the area under the curve, okay? These 2 areas under the curve are exactly the same. They represent the number of molecules. So the higher the peak, the greater the area. So we would say that at this lower temperature, the average kinetic energy is somewhere right here, right below the peak. As we increase the temperature, in any beaker of water, when I look at this, some molecules are going fast, some are going slow, but there's an average kinetic energy, an average speed. And so as you increase the temperature, you still have some slow ones, but you make some faster ones. And so the peak shifts left, but because the range is spreading out, the area has to stay the same. So the peak is lowered a little bit. Okay, does that make sense? Because the areas are the same, because it's the same gas, it's the same number of molecules, but because the range is spreading out more, the height comes down. So this is called a Maxwell-Boltzmann temperature distribution graph. Maxwell-Boltzmann temperature. Maxwell is the same guy that came up with electromagnetic radiation back in chapter 4 when we were studying light.
Man, you just had an exciting life.
Coming up with all kinds of stuff. Okay? He was a mathematician. He figured stuff out mathematically. Okay? And so when we look at this, we're increasing. So now the average kinetic energy at the higher temperature is over here. So this is just showing that as you increase the temperature, you increase the average kinetic energy. So now here is the minimum kinetic energy required for escape of molecules from the surface. What do we call the escape of molecules from the surface?
Evaporation.
Evaporation. So what happens to the rate of evaporation at a higher temperature? It goes quicker because more molecules have enough energy to overcome the attractive forces and they can evaporate faster. Okay? So we should be able to interpret this graph in that this is the higher temperature, more molecules, the kinetic energy is greater at the higher temperature as the peak, the greatest number of molecules are going to have this much kinetic energy here, whereas the greatest number of molecules that have this much kinetic energy there. Okay? This is one of my favorite graphs in AP Chemistry. We talked about this probably 10, 12 different times. It's a good one. So Maxwell had an exciting life. Boltzmann, in the early 1900s, was a big proponent of atoms. The matter was made up of atoms, but science you couldn't see an atom, you couldn't do anything in science, and the church both said there's no way that God's creation can just be made up of these tiny, indescribable particles. And so he was kind of ostracized from the scientific community. Well, that coupled with his history of mental disease, he ended up hanging himself in 1906. When in 1905, Einstein had written one of his first famous papers proving the existence of atoms and how big, or actually how small they were. But because Al Gore hadn't invented the internet yet, okay, that's a joke. You guys are too young to understand that.
He was the environmental dude.
Yeah, but he ran for president and he kind of would brag on how he started the internet. Which, anyway, you gotta be old enough to understand that. At least you guys kind of know Al Gore, maybe. He was the vice president of the United States for 8 years. With Clinton. Okay? Anyway, I digress. This is why we don't get finished right here. But, you know, I can't help myself. All right. So Maxwell-Boltzmann temperature distribution graph. Okay. But life lesson. You see, Einstein had already given the answer and proven Boltzmann correct. But Boltzmann wasn't patient enough to wait for the answer, wait for the solution. And he made a very selfish, poor choice. Now again, he was battling mental disease, mental illness, and that was bad. But I'm telling you that sometimes things look hopeless. Sometimes things look like there is no solution, but the solution is really probably already there. You just haven't found it yet. So be patient. Don't make rash decisions. Okay? Don't make silly decisions. Don't even think about ending your life. It's not worth it. Okay? There's a lot more there. That's just, to me, 1906, 1905, if he had just known, you know, who else, what, he could have done so much more. So he was a very, genius guy.
This is not even chemistry class.
That's a little
It's like
history.
life lessons.
It's just life lesson.
History.
Psychology.
So
Philosophy.
I'll continue on in the life lesson here. I can't help myself because this is what I believe in prayer. When you pray, God is not limited to time. We're walking out a timeline. When you pray, I believe God answers a prayer immediately. Puts it in our timeline. We just sometimes have to walk it out until we get to there. So it's not always instantaneous
That makes sense.
as far as us experiencing it, but it's there. The answer's there. It's always there. Okay, now I'll go on. turn the page.
Deep.
As Bob Seger says, let's turn the page. You guys probably don't even know who Bob Seger is.
Bob Seger.
Yeah.
Bob Seger, the Silver Bullet Band.
Okay.
All right, the escape of molecules through tiny openings. Okay, so we have diffusion as the natural spreading out of a gas. Have you ever noticed if you just buy a cheap balloon and you fill it up with helium, what happens to it the next day?
Deflated.
It's deflated, right? Where did the helium go?
Out the tiny.
Out the tiny pores. Latex balloons, the cheap balloons, actually have little tiny pores. Now, air molecules, oxygen and nitrogen, are really a little bit too big to get through those tiny holes. But the helium is one of the smallest of all the atoms. Therefore, it can kind of fit through those tiny pores and it leaks out. Okay, it's not like you have a hole in the balloon. It's actually, well, you have a bazillion holes in the balloon. It's just the helium can leak out. When you do that, I'll give somebody a nickel if they know the answer, what the word is describing it.
I feel like I knew it at one point, but.
What does it start with?
It rhymes with diffusion.
Infusion.
Do what?
Infusion.
Close.
Effusion.
What did you say, Sam?
Effusion.
No? Okay, I don't know the nickel, so I'm gonna go ahead and put it. Okay? Surface of liquid is called effusion. You guys were so close.
Should take a look.
Effusion. Okay? That's why you have to buy the latex, the mylar balloons for helium, because it doesn't have the tiny pores, so the helium stays. It can only leak out very, very slowly through the little bag.
Are we on number 9 or 10?
Oh,
Evaporation.
well, I missed the top part, but
Pores.
Goes in
and
evaporation.
10 is Effusion.
escape of molecules through, no, we're on 9. Did I put it in 10?
Yeah.
Oh, yeah. Okay, so it's effusion is the one above it. The escape tiny particles. I saw it here, okay?
Wait, 9 is pores and I thought it was faster.
No, 9 is the escape of molecules through tiny openings. It's called effusion.
Oh.
It's called pores.
Now, again, is a little kid or me gonna get through a doggy door easier?
How fast is
A
it?
little.
Okay? So again, it's logical. If you have a big mass, you ain't going fast, and if you have a big mass, you're not getting out of the tiny opening quickly. Okay? Smaller, lighter molecules are going to be able to escape through the tiny pores a lot faster. Okay? So smaller, lighter molecules will escape through the tiny opening faster than bigger. I mean, that's just so logical, you don't even have to hardly write it down. I guess that's why I just skipped it. Okay. So what's the escape of high-speed molecules from the surface called?
Evaporation.
Evaporation. The weaker the attractive forces between the molecules. So if you have weak attractive forces, is it going to evaporate faster or slower than something with stronger? Faster. Okay? The faster the rate of escape. The word volatile. What do you think that means?
Evaporate quickly.
Okay, that's evaporates quickly. We sometimes think of it as being explosive. Ooh, he's got a volatile temper. But that means that this temper goes off quickly. Violent would be, he has a violent temper, meaning he's, an angry man. And so, volatile liquids are liquids that evaporate quickly. So we can measure the rate, or we can predict the rate of evaporation based upon the strength of attractive forces. Alcohol has weaker attractive forces than water. Therefore, alcohol evaporates way faster than the water does.
So is liquid nitrogen?
Liquid nitrogen has very, 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 very weak attractive forces. So at room temperature, you're way above its boiling point, so it's like pouring water onto a hot skillet. It just wants to turn into a gas just super fast. All right, this is where we're going to end the day. Pressure is caused by collisions of gas particles with, what causes pressure other than my test?
Those don't cause pressure, those just cause anxiety and stress. Pressure is when you're worried about doing
Okay,
something.
so this can, have I not opened it yet? This can is under pressure. It's a cleaner just for like a keyboard. Why is there pressure inside this can?
It's compressed gas.
It is a compressed gas. There's a bunch of gas in there, but what's actually causing the pressure?
It's forcing out, it's less concentrated than it is in the mouth, it's forced, it's trying to get the less dense.
It's so
Kind of.
that it wants to-
There is no oxygen, but oxygen, I mean, you can have things with pressure with or without oxygen. What do you think's causing the actual pressure? When I blow up a balloon, what causes the balloon to expand? The air going in. But let's get down onto a small molecular level and think about the air going in. What's the air doing once it's in there? If the balloon is being pushed out, what has to be happening? Air has to be pushing against it, right? Pressure is caused by collisions of the gas molecules with the container wall. It's as they collide with the walls, they're putting pressure on it, they're putting a force on it, forcing it out. Now the can doesn't expand like a balloon does. So the more you put in here, the more pressure that builds.
So how come when you flip it upside down,
Okay, just because the gas is all up here, okay?
Bruh.
You don't know that?
No, I didn't know that.
I don't know.
Okay,
Kinda cool.
so what goes here?
Container wall.
Container wall, okay? So, to increase pressure, we have to increase collisions. We can do that in two ways. You increase the concentration, you put more. That's like you normally think about is that, you know, if your tire pressure light comes on, like you got low pressure in your car tire, you go to this gas station or you go to your garage and you put more air into it and it makes greater pressure. Why will putting more molecules in have greater pressure?
It's the same amount of space if there's more in there.
So what's going to be more? There's going to be more collisions, causing more pressure. But more collisions. It's all about collisions. Okay? First is increase the concentration. This can be done by adding more gas. What we just said. Or how else can we increase the concentration? How does a bicycle pump work?
Push down,
You push down, so what are you doing?
decreasing the volume.
Decreasing the volume, which then makes the same number of molecules in a smaller space. So in essence, you're increasing the concentration so there'll be more molecules hitting any part of the wall at any given time. Right? So you increase concentration either by putting more gas in or by having a piston and making the container smaller. Or by decreasing the volume of the container. The second way to increase pressure is to do what to temperature?
Increase.
What do we, I kind of heard, all I heard was increase.
Increase.
Increase. Now, I don't recommend this. When I was growing up, I lived in a small farm town in Illinois, and we had a big trash burn barrel out in our backyard. Okay, we burned the trash. And back then, we had Right Guard spray as a deodorant. It was a aerosol can. It wasn't the roll-on stuff, it was the spray. But when that can got empty, we could throw it into the fire.
Oh, that's
cans don't expand. You heat it up, increase the pressure, until finally the can can't hold the pressure any longer, and it goes boom. Okay, now, don't throw it into a bonfire, because then it comes like a hand grenade, you know, and it shoots metal shards and hot coals and everything else everywhere. So don't get an idea to try to do that. In a burn barrel, everything's contained, and anything that would go up, not out. Okay, so so it was a much more controlled environment, but it was still a big boom. But when you increase the temperature, now it does two things in terms of collisions. This is the best part. If you increase the temperature, what are you doing to the speed of the molecules?
Move faster.
They're moving faster. So what does that mean about collisions? You're going to have more collisions, will move faster. The temperature which makes the gas move faster, and hit the container walls with more force. But you're also, because they're moving faster, you're also going to have more collisions. Which is why if you get a speeding ticket, insurance companies say your insurance rates are going to go up, because the faster you're going, the more likely you are to collide, get in a wreck. Okay? And so it's all about collision. So when we come in tomorrow, we're going to talk about how do we measure pressure then. Okay? How do we measure pressure? Oh, I gave it out of the way. I didn't have much to
Good shape.